Hi everyone, my name is Sebastien Jourdain. I'm a distinguished engineer at the scientific team in Kitware, and I'd like to welcome you to a webinar on VTK.wasm. Next slide. Thanks. So I will kick things off today with a quick introduction to Kitware, and then I'll turn things over to Jaswant, who will go over an introduction to VTK.wasm, what it is, and how we set it up so it can be used in many ways without the burden of building your own package. For reference, Jaswant is a senior R&D engineer at Kitware who made that VTK.wasm package a reality. We've got other people also working on it in the background, but most of it is coming from him. So you will get everything from the prime there. So after his introduction to VTK.wasm, Jaswant will go over various usage across languages and tools so that new VTK.wasm packages, just to cover that new VTK.wasm packages. If at any point during our presentations you have questions, feel free to type it in the chat windows for this live stream. We'll take a break for questions at the end during the presentations, but also depending the flow, we will interrupt and either I will ask Jaswant those questions, or while I will be talking, Jaswant will ask those questions to me. Next slide. Kitware was founded in 1998 and currently have about 220 employees across the US and in Europe. We primarily perform software and AI research and development services for customers in government, industry, and academia. More people knows about our popular open source platform like CMake, VTK, ITK, and Preview than they do about Kitware. We are proud of our long history of accomplishments in open source and open science, as it lines up well with our visions of making the working a safer, healthier, better informed place. And since 2020, we are now 100% employee owned. Next slide. At our heart, we are a highly collaborative company. Our largest research efforts are generally funded by the US federal government and involve many commercials and academic partners. We are also involved in many smaller research efforts. We perform custom application development, and we provide support and training on our various open source platforms. Our area of expertise span healthcare and life sciences, which includes our work on digital pathology that you will hear in previous webinar if you're interested in, medical visualization, bioinformatics, and scientific computing, where VTK has been designed from. We also work in energy and manufacturing with a focus on simulation workflow, high-performance computing, scientific visualization, and data analysis. For defense and intelligence customer work in image and video forensic, threat detections, and activity recognitions. Deep learning is a large part of what we do. We have a strong emphasis on ethical and explainable AI. Next slide, please. Most people know Kitware because we have used one of the open source platforms that we have helped to create and maintain. We have a strong commitment to open source and open science at Kitware, and put considerable effort into building vibrant community around our platform, supporting this community, publishing our results, and encouraging collaboration throughout open source. You can find more information about all of those platforms and technology in our website. In this webinar, we will focus on VTK.wasm. Before I turn the presentation over to Jaswant to tell us more about VTK.wasm, I want to remind you that any questions you have can be typed into the chat for the live stream, and I will ask them, or Jaswant will ask them to me later on. Go ahead, Jaswant.
Thanks for the introduction to Kitware and my introduction as well, Seb. So let's start off with this. So VTK.wasm it's a thing that's been in the pipeline for more than 3 years. It provides the C++ library that you may have been familiar with on the web. It's not VTK.js. This is a different thing. It's the same as VTK. So what do we provide for that, right? We compile VTK C++ to WASM, and we bundle that, and we provide it with official releases and even with nightly builds of VTK. So there is a systematic process that we have in place that builds VTK using the toolchain and publishes it to the package registry. And all of this encapsulates almost everything you need to render and load data sets and do some visualization. A key feature of VTK.wasm is it's a small API. It's designed to be efficient for communication between the client, that's the web browser, and the server. The architecture that we made, it allows you to mirror the scene on the server side. It allows you to mirror that exact scene on the client using a state/blob system, which observes for method calls and interaction events that happen. For JavaScript developers, there is a very nice API that allows for object creation and updates using observers and method calls. So you can set properties on these objects very easily. And you can also make method calls with various kinds of arguments. This gives you a kind of native feel when you're working with VTK.wasm in a JavaScript environment. If some of you have used VTK.js, it should be very similar to that. The API also includes a native API for an object manager that works with the state/blob system. It's okay if you did not understand what I just said. It's mostly for the more expert developers who want to work with the native API to build on top of it and make better visualizations that are more powerful. We are actively working on a new rendering backend that's based on WebGPU. It's still a work in progress. It supports rendering surface meshes, that is, meshes made of polygons or triangles or quadrilaterals. Currently, it does not support volume rendering, but we are working towards that goal. And this will allow us to leverage modern GPU capabilities directly in the browser. We expect this to be ready by the end of 2025. The architecture includes an add-on infrastructure that simplifies the process of serializing and deserializing VTK objects. This allows for easy data transfer and scene management. What this means is if you extended VTK in C++, you could bring that into the system to VTK.wasm, and you can still use the same application that you had before. To ensure the quality and reliability of VTK.wasm, as I said before, we have a very systematic process. It's all integrated in our CI pipelines that automatically build and test the WASM bundles, and this helped us maintain a stable and robust platform. So you remember I used the jargon of words, object manager, states, blobs. So that is a core architecture that allows us to keep WASM objects in your browser in sync with the server-side object that you have running on a GPU server. So the core architecture of VTK.wasm is based on very few key components. At the heart of it is this guy. It's called the object manager, which is used to register VTK objects for tracking their states. This architecture uses a context with serializers and deserializers to manage the state of objects, including both strong and weak objects. For example, if you have a render window, a VTK render window, and that render window has a renderer, and the renderer has a couple of actors. Over here, you would give your render window to the object manager, and the object manager would treat that render window as a strong object, and the dependent objects of the render window, that is the renderer, the actors, the mappers, all of those are weak objects, so they are also tracked by this manager. And we essentially created the serialization, deserialization code. It's generated automatically using macros. It's using the same system that we use to wrap VTK C++ for Python. For rendering, there's a WebGPU backend that's currently in development, as I said before, and this new system, the object manager, it is also capable of serializing and deserializing your render window if you were using the WebGPU render window. Let me talk very little bit on how you can use Kitware's existing tools and CMake infrastructure to compile your own C++ code. So for doing this, first, let's just talk about the benefits of doing that. By compiling your own code, you get a much more smaller, more focused WASM bundle. The default bundle that we provide, it includes more than 15 or 16 modules. It sums up to almost 50 to 60 megabytes. Now, on the web, you want to keep things small and focused. So if you compile your own C++ code, you could have a tighter control on what gets into that WASM bundle by only choosing a few modules. And this helps reduce the overall size of your application. You can also expose a more specific API to the JavaScript side using things like mscript and binding generator. Kitware also provides a Docker image to help with that. So the Docker image, it's called VTK.wasm SDK. It includes a compiled VTK installation. It also includes CMake, Ninja, and Node.js, and mscript. Basically, it has everything you need to start compiling your code for WASM. And now I will show you a WASM application that we built. Now, there are multiple architectures on how you can design your WASM application. We will cover those in dedicated courses. You can reach out to us for the course, and we will talk about those different approaches. This application that you're seeing on this slide, it's called a geometry viewer. Its core is implemented in C++. So inside C++, we are creating a reader, a mapper, an actor, connecting the pipeline and rendering it. And it exposes JavaScript entry points. And these are functions that either take strings or booleans or numbers. So if you want to load a file, you pass the name of the file. If you want to change the color to something, you pass 3 integers or doubles. And if you want to enable edge visibility, you pass a boolean. So these kind of functions are exposed. So let's go to the demo. I'll stop sharing this. And let's see if I can share the other tab.
And while you are sharing, I just want to add something on the VTK.wasm bundle that we are creating. When Jaswant say it's going to be 50 megs or 20 meg or something, this is the non-compressed versions. Usually when we compress the data or the WASM bundle, it's way smaller. And also something coming up that we are going to cover at the end is that the goal of being to break down the VTK module, so we'll be able to load only the modules you need. So the fear of a big bundle is not going to be a problem very, very soon. So go ahead, Jaswant.
Thanks. So this website, it will be shared in the slides, and you will also see it available in many of our blog posts. What this does is it builds a couple of C++ applications that are actually in VTK repository. It builds them and it lays them out like this, and all these are really interactive. So they're not just images, you can interact with them. And it is running VTK C++ inside this application. And I have many of these over here. Some of them, it will say no preview available because it cannot run in an iframe. So that's what all these are, essentially, they're an iframe. So now I'm going to go to the geometry viewer WebGPU. I have that. Let me open that here.
Yeah, it's not showing the, yep, good.
So this is by default, the URL. So this application, you can customize it via query parameters. So the view API, I'm giving it as WebGPU. And you guys can go and see in the code how I'm actually using that parameter to activate WebGPU and VTK. And this application is getting data from a URL, right? And then it has a couple of other parameters. So you could, there are many controls over here. For example, you can change the color, color by array. I made it solid. You can also change the background color. So every time I make a change here, it's triggering a function in JavaScript that is wrapped to a C++ function, which is manipulating VTK objects. So you can also open files in this application. It supports all the data. It supports unstructured grids. It just extracts the surface of the unstructured grid. It also supports partition dataset collections. That's why you have a choose directory. But now I'm just going to open, for example, this planetary gears file, right? And you can do a lot of things. You can change the representation to a wireframe. Right now, the background is the same, so you cannot see it, but there it is. I'll change it back to surface, enable edge visibility. No, that's what it's visibility. Enable edge visibility. And you can also color by different arrays. So there are not many color maps over here. I only put the default. We only provide the default color maps that are in VTK, which is a very small subset. So this just shows what is possible. I mean, this here is a full-blown geometry viewer, right? You can open almost any kind of files, and you can even inspect the connectivity of each cell. So I think this is pretty cool because all of this is using VTK C++, and you don't have to write a brand new reader. If your reader is in VTK, you have it here. So that's one thing I wanted to show. So I will stop sharing this and go back to this tab. And I will hand it over to Seb, who will cover the integration of VTK.wasm with Python and trame.
Yeah, thanks, Jaswant. I let you get the slide.
Yeah.
So in the beginning of the slides, Jaswant introduced the concept of client server and so on. And most of the work was originally driven by the need of trame, where we've got a Python server doing most of the heavy lifting and wanted the capability to offload the rendering to use the GPU of the thing that is happening on the client side easily and transparently. So just for those who don't know what trame is, trame allows to create web application in plain Python. And VTK.wasm is just used inside trame VTK local, which is one of the Python package that you can install along trame to create a widget that is capable of exposing the VTK render window that you have available on the server side using the regular Python API onto the client in the browser. And by doing that, basically, that widget abstracts the scene synchronizations and method calls between the server and the client. So technically, you just write your Python code as usual. You just say, here is my render window that I want to see in this location in my web UI. And then from time to time, when you interact with the scene, add new actors, change the filtering parameters, or do things in your 3D scenes, you just ask the widgets to update. And then automatically, only the delta will be sent from the server to the client using the infrastructure that Jaswant described earlier with serializations and so on. In terms of capabilities of the widgets, we can evaluate the client state, or meaning the VTK state that exists in the WASM to extract the informations and have that available on the server side. Typically, you want to do like some picking or knowing where the mouse is or knowing what's the camera locations and so on. You can add observer or evaluate things that can ask questions on the current state that only exists on the client side. You've got the infrastructure to synchronize the scene content, and then you can also export the scene altogether and make a standalone file that can be used to be displayed in stateless systems with a scene viewer that we will talk about later. We can also invoke method on the client side through using the actual object on the server side. Next slide, please. Or although there might be a question.
Yeah, there are some questions in this webinar. As I just saw them. First question is how the speed and computations compare to WebGL or other competitors. So this question could mean a lot of things. So I will just try to answer it the way I interpret it. VTK does use WebGL because VTK was traditionally using OpenGL, and when you compile anything that's using OpenGL in C++ to the WASM, mscripten makes a map of the OpenGL function calls and translates them to WebGL. So VTK is actually using WebGL, and I wouldn't say you could compare it because VTK is kind of a middleware, but sometimes VTK does things that may get in the way of your rendering pipeline, and those kind of use cases, using WebGL directly may be the best for you. But the thing about VTK is we cover a lot of use cases in general visualization, and we handle those things pretty robustly, so it should be good. And the second question is, are these demos available at a link, and where can we interact with them? So I am sending the links in the chat. I hope that everyone will be able to see them. Is that right, or is it just the presenters?
I'm not sure, but either way, at the end of the webinar, there will be a follow-up email, and all the links and everything will be provided along with the presentations. That has some of those links anyway.
And another question those observers are synced between client servers, so we can register an observer on the widget, for example, and have an observer on the server side called React, question mark, for example, interacting with a plain widget. Yeah, Seb, I think you can answer that much better than I can.
I will. I won't answer it right now because I do have that exact example later on with the slides and so on. But yeah, we definitely can do that. Yeah. So I guess we can move on to the next slide.
Okay.
Jaswant. Okay. So again, in Trame, the way you do things, you create some widgets. That's what you see here in some code sample. By default, many of the depot rely on remote rendering, where the server is doing the image computation, send the image on the client. And that's what you can see on the top left of that slide is like this widget that we use generally is just like we create a remote view, we give the render window, and then we grab some method that we want to be able to do with that widget, meaning that the scene has changed, let's update. Oh, I want to reset the camera, I want to be able to call reset camera. And as you can see at on the bottom sections of that slide, it's exactly the same thing, but this time with VTK.wasm. So the top one is sending images. The bottom one is using VTK.wasm to do rendering locally. And the only difference is that some parameters are slightly different. The first one, you adjust the image size when you're interacting or not. And then on the local view for the WASM, we are some control on the throttling rate that we want to adjust. Because keep in mind that if you are updating a filter very often that change the geometry very often, you may oversubscribe the network or have some latency happening when that synchronization is happening. So what we did was provide you a method that will automatically throttle the update rate. So every time you ask to update the view because the scene has changed, we won't do it more than 20 times per second. And that allows us to keep things very smooth and so on. Next slide, please. So the questions we just had about widgets and observer, this is one of the example. And you can see that there's a URL at the bottom. It might be long to catch it from the video, but again, you will get the link at the end through an email follow-up. So here you can see that the first block is the same thing as I was showing, where you can define the widgets, you bind the render window that you care about, and then from the Trame point of view, you can start adding some listeners for a plain widget state that will trigger or execute the functions in Python when that objects change. And at that point, you can like get your origin and normal, update your cutting plane, and just ask to update the view. And in terms of listeners, the way you define your listeners is that you will provide the WASM ID of your actual object. So there's ways for you to get the information about what's the ID of that given object in the WASM world. And then what is the VTK event that you want to listen to. And then after that is what is the variable state that you want to update by interrogating the actual WASM state. So in this case, we are going to grab the object with that WASM ID, get the widget representation, grab the origin, and use that to store the value into the origin field of the plain widget state. And the same thing for the normal. And by doing or by defining those listeners, you can dynamically add and remove those listeners with Trame. You will be able to easily sync up those widgets with the processing that you aim to do on the server side. I see lots of questions popping up, but Jaswant, is there anything that we should focus on right now?
I don't think so. Let me check. So there is a question that says they have an existing Trame project that utilizes local view Is it already using VTK.wasm, or do I have to specifically enable it to use WASM?
Oh, that's a good question. So if you are using trame VTK on which you get that local view is actually using VTK.js. But if you want to use VTK.wasm, the only thing you need to do is pip install trame-VTK local and use that VTK local namespace to create your local view from that package. And also in terms of VTK versions, you need 9.4 minimum, ideally 9.5. And we are still making more progress on the nightly one. So there's more and more capability coming almost every week on the WASM side. Hopefully I've answered that questions, but there's nothing specific. You just pip install it. The package from Trame will figure out exactly what is the VTK versions you depends on or you have in your Python environment. It will download the WASM package compatible with that specific versions and use that for your web UI. Next slide.
Yeah.
So the next example, again, there's lots of text here and so on. So don't worry too much about like understanding all of that. Actually, all of those web pages provided at the bottom of those slides cover and explain more details of what's happening there. But in a nutshell, what we have in that Trame example here is all you can do picking. And the difference between like widget interactions and picking in VTK is that you need more than just listeners. You need the capability to be able to call methods on the WASM side to say, oh, here is my XY coordinates. What is the thing underneath? And you will get an actor or something else, depending on the picker you choose. But technically, you need to make some method calls. And the piece of code that I've highlighted in that slides kind of covers how you can do that directly in pure Python, even though things lives on the client side. So you can like make the request and get your actual object mapping between the server side and the client side. So there's like some listeners to capture that XY. Once we get the XY on the server side, we submit a request of on the picker using our server-side instance of the picker to pick with the renderer and so on. At that point, if the picking worked, we can ask to get the actors on the picker that have been picked, and then we can start like swapping some of the properties so we can highlight the given actors and so on. You can go to the next slide unless there's
before
questions.
we go to the next slide, there is one question. If a filter pipeline on the server side is feeding data to a mapper, and if that whole filter pipeline is regularly updating, will that synchronize efficiently to the client-side renderer? Is it asynchronous? Is it just updating that data for that specific mapper?
Yes, so yes to all of that. So it is asynchronous because you got two processes, the server and the client. Technically, every time you execute a filter, you need to tell the view widgets thing to update. That's why we have the throttling that I was mentioning before. And whatever is going to be sent is only the delta, meaning that if, like you said, the mapper or the filter is just changing the field, but the topology and the points are the same on the actual poly data, those will remain the same. So we won't send them again. We'll just send new arrays that are different and that are getting used for the visualization.
Okay.
And I see one question. Yeah, all of that will be recorded so you can like replay the video later
on. There was another question. Where do you recommend executing the pick, server side or client side? If my server is running without a GPU, the pick may not work well. Or do you think that is fine?
So Actually, the pick is always going to happen on the client side in the context of VTK.wasm, because VTK.wasm is the only one who owns the full scene and has the rendering. There's no rendering happening on the server side. But because with trame, you define the full visualization using your VTK object on the server side, you have your instance of your renderer, you have your instance of your picker. So it is convenient for you to kind of ask, can you make that method call with those objects? But that method call is going to be executed on the client side and give you back the information you need on the server side.
Yeah, it depends on the use case, right? Depending on the use case, one of them will be better than the other. So it all boils down to that.
That's true, but it would be more like if you do remote rendering versus local rendering. In the VTK.wasm use cases, it's always local rendering, so we don't have the scene necessarily on the server side. I mean, we do have it, and if we do like raycasting as a compute rather than a hardware picking, we could do those picking on the server side, assuming the camera is in sync also, because the XY of your camera client side might not be your XY on the server side pointing to the same thing, because we don't necessarily keep the camera in sync.
Another question that asks whether it's possible to run trame applications using Pyodide. And from what they've tried in the past, it wasn't possible to install VTK in Pyodide.
Yeah, we are not there yet. I don't think it's impossible, but there's definitely non-negligible work to start enabling that in Pyodide as of today. And for trame, running trame in Pyodide, again, there's a path that we can take to make that happen, but like the implicit WebSocket communications happening between the JavaScript and server Python will have to be reworked so we can use our own communications between those two environments. So it's possible, but it's not available as of today. Oh, okay, so the next slide, so that kind of wraps up the trame part where the goal was to be able to write just Python code and use VTK.wasm to offload the rendering to the client side. At the beginning, we talked about the fact that we can do C++, Python, and JavaScripts. Now we are talking about JavaScripts. And while we are still using the same underlying infrastructure with some serializations and some infrastructure of object manager and so on, what we managed to do with the VTK.wasm for JavaScript is to build a nicer API for object creations and manipulations. Technically, it looks very much like Python. What you will get is a VTK namespace or VTK object on which you can like instantiate a VTK polydata mapper, VTK actors, any kind of thing that belong to the VTK namespace. Those will be actual JavaScript objects. They are technically proxy that are going to forward calls underneath the cover, but to some extent, those are regular objects on which you can call methods. All the methods so far are asynchronous, so you need to await for them because we do have some constraints. Some of those methods must be asynchronous and some are not necessarily asynchronous, but for simplicity, we are forcing everything to be asynchronous. What you can do is the same thing as what we have in Python nowadays is like even in the constructor of the object, you can directly pass the properties that you want to do. That's why on the third line of the first block, we can create the VTK actor and directly bind it to a mapper, because the property mapper of the actor is going to be that same instance of that VTK polydata mapper. The other thing you can do is start observing objects. So technically, you can grab an instance of a render window that you've instantiated, and then you can start calling observe, provide the string of the VTK event name there, and have a callback on which you can start doing things. In this example, on the renderer, we are directly accessing the active camera as a property. So it's just dot notations with camel case. And then on that active camera, we also go through and ask the property position. So we'll be able to just print in the console the positions of the camera while the render window is while we are interacting with the render window. We can easily set property in the same way as reading them. So on the third block, you can see that with the edge visibility, we can turn it to true, or in the command, we can also make the method call where we say actor get property. We need to await for that, and then set edge visibility to true and await for that. The nice things with those property settings is that they are synchronous, while any method call, you need to wait for them. The other cool thing that we have is if you start building data arrays for VTK points, connectivities, or scalars, you can use directly typed array to bind those memory space with the given value. And finally, for the render window, you want to have a canvas selector to say where do you want to bind your rendering into your DOM element, so you can define the space and fill that up. And at the end, I think you need to start the interactors, and that's about it. So it really looks like VTK Python, but in pure JavaScript. I see lots of questions, but I didn't get a chance to read them. Jaswant, is there anything that I should cover before moving to the next slide?
No, there was interest in, there was this question, I answered it to the best of my knowledge. They asked, can you render unstructured 3D grids similar to the geometry viewer example you shared earlier, but for time series meshes like reservoir simulations?
I would think so, yeah. I mean, with VTK.wasm, you really get all of VTK. So the geometry filters and so on are part of the system. So it's just a matter of updating the data arrays of your source or readers if you want to play the time, for instance. Keep in mind that if you're building a pure JavaScript applications, you still need the data to be in your browser to do things. If you have a client-server infrastructure, you still need to be able to ship the arrays to the client. And to get back to one of the questions we had before about how efficient things get done in order to synchronize a remote scene versus a client scene. For example, a reservoir uses 3D cells, so it's an unstructured grid. It's a fairly large model. When we do rendering, we just care about the outside of the surface. So technically, what would happen when we move from one step to another using VTK.wasm in the context of trame, for instance, is that the geometry extraction will still happen on the server side, and then only the skin array of the field that you want to display through time is going to be sent to the client. So it won't be the full 3D mesh data array that will be sent over. It will be just a subset of that geometry that you're currently seeing. Anything else, Jaswant?
Nope, I think we can continue.
Cool. So earlier I mentioned on the VTK local widgets from trame that we have the capability to dump and save the scene that we're currently looking into a given file. And what you can do with that file is that you can use our standalone scene viewer that lets you just share very easily the visualization that you have. And the HTML code that you can see is exactly doing that, meaning that we just import the scripts. I think we might want to update the URL. I think it's the old one because we end up publishing all the VTK.wasm as its own NPM package. Before it was part of the tram package, and I still see that tram VTK local there. But other than that, you can grab that library very easily from a URL, fill sections of your page and just create a viewer that will download a file format that is technically a zip file with a mix of state and blob binary representations, and then it will be able to render that in the browser. And we have the options to choose between WebGL and WebGPU. But like Jaswant said, WebGPU is still work in progress, but it's already available as of today. Next slide. So now we've got a questions for you. Which part of VTK.wasm are you interested in? Is it C++ to the web? Is it the JavaScript API? Is it the local rendering with trams and therefore Python? Is it standalone viewer to showcase complex VTK scene for collaboration, exchanging things? Or is it something else? And for the something else, it would be great if you can like put it in the questions so we can track that down and maybe provide some feedback on that. Cool, and we see the overlays of the progress for everyone.
Yep.
So lots of people are interested mostly in C++ to web, but there's definitely some JavaScript and Python usage, obviously. Cool.
There is a question that asks, is VTK.js going to be deprecated?
Not necessarily, because VTK.js still has like a strong usage. It doesn't have the same capabilities as VTK.wasm in many ways. We are catching up in terms of capabilities. I would say that it really depends, and I think we can't give you like a general answer, but I would have a tendency to say that if there's a new project coming in with what we have in plan for VTK.wasm, I will definitely start with VTK.wasm, even if you want to do like pure JavaScript usage, because you will get so much more capability out of the box. So that will be my take. You can go to the next slide, Jaswant.
Yeah, so as we said, WebGPU was still a work in progress, and we expect WebGPU to land towards the end of 2025. That's very soon. And we have lots of work to do, but it's exciting. And we are also thinking about ParaView integration. So ParaView is a graphical application that has VTK as a 3D engine. So it does override some behavior. It has its own set of VTK classes, and those need to be taught how to serialize and reserialize. So we expect that to happen some point within the next year. And it's listed over here that the custom VTK class compiled and registered on this side. So that is already supported. We are just improving the library integration so that you just have to import your module in Python, from my custom module, import my custom filter or something, and that import itself would register the serialization, deserialization routines, and you don't have to do anything. But in the current approach, you actually have to call an explicit method that tells the object manager, I imported a new class, here are the serializers for that. So that is still work in progress, but it's getting improved. And we also plan to support more VTK modules. There, as I said, there are already 16 to 17 modules that are supported. We still have more work to do for some of the rendering modules, like volume rendering and rendering LOD, and these are very less used modules, but we have to look at them. And we are also interested in dynamic loading, so that our WASM bundle that we distribute, it'll be very, very small, and dynamically based on what you're importing in your JavaScript, it would fetch the VTK WASM module. So for example, if you're using stuff only from rendering core, it would only get rendering core and maybe OpenGL or WebGPU. But if suddenly you start using a scalar bar or something else that's living in rendering annotation, it would only get rendering annotation then. Right now, the ship bundle has everything, so that's why it's pretty huge.
Yeah, there's a quick questions. What is the relationship between WebGPU and WebAssembly, Jaswant?
Okay, so WebAssembly is I can explain it with analogy. So think of WebAssembly like C++, or actually think of WebAssembly like native x86-64 assembly, right? Because you can compile a lot of languages to WebAssembly. C++ goes to WASM, C goes to WASM, Rust goes to WASM. WebGPU is actually nothing related to WebAssembly. It's just a graphics API that has about 20 to 22 functions that allow you to draw triangles on the screen or do computations on the GPU. So think of WebGPU like WebGL. It's just a better, more smaller API than WebGL. So they are different. Yeah, go ahead.
I was just going to say there's another question. I think you answered that. They are different, but it's a more modern rendering API that is providing access to the GPU in a more efficient way. The next question that we have is, can you talk about what things are expected to not work with WebGPU, which is expected by the end of the calendar year?
Yeah, so the roadmap is currently on a Discourse community post. It will be updated, but I will quickly read it out and then drop a link in the answer. So right now, what is supported? You can use WebGPU on 2 platforms. If your app is targeting Linux, it can try WebGPU using the X11 backend that we added. If your app is in WebAssembly, you can use WebGPU. So this is just to bring up a render window. For actually drawing something, it can only draw surface meshes. So VTK polydata mapper, that's the only mapper that works at the moment. Text rendering does not work because we haven't implemented it, but you could create text using the VTK text source, where you pass a string and it will generate polydata to represent your text. That's one way to render text. Volume rendering is also not supported yet in WebGPU. But as I said, there's already the polydata mapper ready, which most people use the polydata mapper. Even if you have a 3D unstructured grid, you just extract the skin of it and it goes to the polydata mapper. You can also do shader customizations on the polydata mapper, just like you did with OpenGL. And it also has a much faster performance because it's using slightly better mechanisms to upload the data. And additionally, I just want to say that all of the things that are not implemented in WebGPU will be done soon. Our goal is to complete most of it by the end of 2025. So that includes adding support for macOS, Windows, and even Wayland and iOS and Android. So I will share the link in this as a reply to this question. So that post should have the details if you want to refer back to it. We will also send this link to you in the post-webinar email. Okay, so the next slide is poll time.
Yeah, which part are you most eager to see coming? Basically, we've talked about the various things: WebGPU, peer-review support, dynamic loading of VTK modules, custom VTK modules, loading, support for more readers, filters. Yeah, just curious to see what you can't wait. Interesting. So WebGPU is definitely one of the leader. Support for more readers and filters is pretty there. It's funny to see not dynamic loading of VTK module, but
seems like nobody cares about the size.
Yeah.
Seems like nobody cares about the size of the application. That's interesting.
Well, anyway, that's going to happen no matter what, but it's good to see like what you really want to see.
Okay, so the next slide is a demo, and I will stop sharing that tab and share my window instead. Share something else. Share this window. So this is our landing page for VTK.wasm. I hope everybody is seeing this. Seb, can you confirm that the address bar is visible?
Yeah, the address bar is visible. Can
Great.
you reload? I don't know why there's some like views that don't show up.
Yeah.
I guess it's loading the data or something. I don't know why it's slow.
Yeah, it was there before. I don't know why this one's not loaded now. So this is a landing page, and we post weekly updates to the activities section. Let me open that in a new page. So this is where you will see all updates that are specific to VTK support for WebAssembly. And each weekly version is the version like the major, minor, and the date it was built. So you can see that it's built of two sections. The first part covers how you install it in Python, right? And you use the extra index URL. And if you use this wheel in trame will automatically download these WASM bundles, because the key over here is your VTK version in Python must match the VTK version in WASM when you're using trame VTK local. And trame already takes care of that for you, so there's not much you need to do for that. We have the guide section over here, and it is split across different kinds of developer. It depends on where you sit. You could be all of them. So for C++ developers, there are various usage patterns, and we cover some of them here. So first of all, how would you build VTK? That is covered in this VTK documentation. So we didn't want to copy that over here, so it directly takes you here. And it is exhaustive. It teaches you how to build VTK.wasm for 32-bit, 64-bit on macOS or Linux, on Windows. And you could basically just copy paste this into your terminal, and you will get to build VTK. And it goes on a little bit more about what's possible, how to run unit tests. So let's go back to the VTK.wasm landing page. And then there's an EM bind section, which teaches you how to expose C functions to JavaScript. That's the most exciting thing. So this function, it's defined in C or C++, and it's accessing this cone source, which is a VTK cone source VTK object, and it's calling some method on it, and it's passing an integer. So that's how it's defined. You need this script keep alive, and it needs to have C linkage. Otherwise, the symbol name gets mangled, and it becomes something like this. And in JavaScript, you have to call this. That's not fun. So that's why we used C linkage that preserves the name of the symbol. But if you want to bind C++ functions or C++ member functions, you can also use mscript bindings and do it this way, or you pass a function pointer directly. And argument parsing is also possible. So let's say you had a traditional C++ VTK app, you could run it on the browser, and you could pass arguments to it. That will be shown in the index, in the HTML page where it set up everything. And this is the VTK setup. It's just like a regular C++ pipeline, right? You have your cone source, you have your actors, render window, and that's it. And then for the canvases, we do some special stuff. Normally, you don't need to do this because your canvas generally has an ID that's canvas. But if you customize it, this is how you would set it on the render windows. And finally, there is some special thing you need to do for the render window interactor to make sure that your interactor is kept alive and your whole pipeline is kept alive. This is only needed if you're using this specific approach. So the full code is also present over here. I will go to the next setup, HTML. So you remember I told you about arguments. This is how you pass arguments. So if you were calling it on the command line, you would type the whole thing in one sentence, in one line. But here you pass the arguments as a list to the WASM module. And that's about it. The main.js is generated by mscript, so we won't see that. And that will load the WASM binary. And then you have the build system on how to build it. And guess what? It's running right here. The same code that I showed you above, it's running right here. This slider, it's linked to call that set cone resolution function. So it's changing the resolution. And this other slider is calling the set height function. So I think that's very neat because we actually use this even to show the VTK examples that are written in C++ on the web. Moving on to the JavaScript developers. Some of this code was already covered by Seb, where you created the VTK objects directly, and you created arrays, and you passed them to VTK objects. So even that is running live, and this is not connected to any server. It's all happening on the client side, on my machine over here. And I think that's very cool. And there are different ways to load that VTK.wasm package, right? That's available on NPM and even on Unpackage. And you can, if you read all of this, you'll find out what you exactly need, and then you can incorporate that into your application. And this is how you would choose between WebGL/WebGPU. The key thing is, if you're using WebGPU, the execution mode has to be async because WebGPU API is async. And this section is for developers who are more comfortable in Python and want to use trame, or people who want to build client-server applications. It walks you through a basic trame app where you're rendering a count, changing some parameters. And it also talks about pushing the camera. So these are additional arguments you can pass to the update, whether you want to push the camera or not. And then it also has the example for the 3D widget, where you have a plain widget that's clipping a typewriter. And ultimately, we have a method call. This is really useful for picking. So you can implement picking in your application, and you can decide whether you want to do it on the client or the server. Finally, I see that we have only 4 minutes left. So I'm going to talk about very quickly about this using VTK.wasm as a data viewer. So if you're using a trame app, you could export the state on the server to a WasX file. This is some extension we made up. It's not existing. It's just something we made up. It stands for WebAssembly zip extension, I think. And in your HTML, you just need these lines, and you provide the ID of the div under which you want the canvas to be placed, and then you give the path to your zip file and the architecture, or the path to where the WASM binary exists, and ultimately the rendering backend. And if you want to generate that WasX file, this is how you would do it. To be extremely simple, let's say you have an app that's doing some clipping, and that's a VTK pipeline. So that's a trame app. So the trame app has this context WASM view, and you call the save function, and you give it path to the file. So this is an example of that. You can see that I'm going to pick, as my mouse is hovering around, it's changing the representation to surface with edges, and it's changing the color of the part that my mouse is on. So this is useful for quick interactive visualizations that you want to share, or you want to do collaboratively with somebody.
Yeah, I just want to add on that example of the picking part. What's happening is that we use that state from the viewer, and then we use the API on the JavaScript side to get our hands on the various WASM objects, start observing things, and making method calls, and that's how we do those swapping automatically. The code is available in the repository and in those examples, but that's also a possibility with the viewer, that you can just say, rather than just viewing and do nothing, you can also add a bunch of JavaScripts up to that and start describing some behavior that you can embed in the standalone viewer that doesn't imply or involve a server. And that really wraps up the website that we've been creating around VTK.wasm to try to document all of that. But Jaswant, I guess we have 2 minutes. I think you've got a video that is pretty cool.
Yeah, I can do that really quickly. Share window.
And what Jaswant is going to show you is some code in pure JavaScript where it described the full pipeline. This only worked on his machine because he had to enable some custom modules and build the WASM on his own, but eventually that's what you will get by default. And so it's just a wavelet pipeline with some contour filters and then some clipping, and all of that written in pure JavaScript, where the slider at the top adjusts the contour, and then the 3D widget drives the clipping, all in pure JavaScript.
All of this is in one single HTML file, so it's very neat. And you're adding observers on the plain widget, and you're connecting the sliders to the number of contours. And this is where we want to take VTK.wasm to. Okay, so that wraps up the presentation.
Yeah, thank you, Jaswant.
Okay. Yep, I think my screen is stuck.
Yep, I don't see your screen. But I guess the last, oh, you're back moving, so
Yeah.
maybe you can share.
Yep.
So again, Kitware can be your partner moving forwards. You've seen what we can do with WASM, but the idea is that we can help you achieve what you want faster. So keep in mind that we are around. We've got lots of resources available for you to interact with us. We've got the website that we just went through. We've got the discourse on VTK. If you are looking for help, support, training, there's a contact for Kitware available, and we'll be more than happy to help you customize or build software with you. So thank you so much for joining today, and hopefully we'll get more news on WASM soon. Is there any other questions that have been like missing? Is there any study showing how fast WASM is compared to other ways? There are some stuff that show that WASM tend to be slightly faster than pure JavaScript because there's less conversions. I don't know if you have any numbers, Jaswant, but
I don't have numbers, but most people say that WASM is fast, but the way you build these applications, it often involves connecting it to JavaScript, and that context switch from WebAssembly to JavaScript, and then let's say you want to call some function, so you have to copy the arguments, you have to convert them into something that WASM can process, right? That is what slows down the application. For WASM as a whole, it's very efficient because the browser engines, they are just in time compiling their WASM straight to x86 64 or ARM64. They're not doing it through a higher level language. So it should be fairly fast. I hope that answers the question.
I think so. And that seems that the question seems to be steady. So I think we can call it the day. So thanks again, everyone, for joining us today, and have a great rest of your day.
Thank you.